recording started. Dr. Mohammed, you can see the recording?
Yes, sure.
Yes, great. My name is Mazen Hilali. I'm a senior petrophysicist with local engineering in South Iraq with the West Gurna 2 project. Because local have another project in Iraq and Nasriya city called Arido. Our lecture of today will be with Mr. Nicolas Kotlar. He's the domain champion for case hall interpretation with KAPPA engineering. I will just share my screen, okay, quickly. So I would like to thanks all the attendees, the tutors, SPWLA committee, Dr. Mohammed Jawad Zain Al-Abidin, for attending this webinar and helping us for this technical event. This webinar will be regarding multi-array production logging tool analysis application in Emeraude software by KAPPA Engineering Company. Mr. Nicolas Kotlar will present this lecture. We have did 6 webinars this year. This is the 7th one with KAPPA this year and the 4th in the last 2 years. And this is really appreciated effort from KAPPA Engineering and from Mr. Nicolas Kotlar. We'll have another 3 webinars hopefully this year with the ISP and GeoActive and TGT hopefully. As usual, we'll give a special certificate for all the attendees that came for 6 webinars and more. And if you like to join our SPWLA Iraq chapter, you are very welcome. Q&A will be at the end of lecture. Okay. Dr. Mohammed, if you the mic for you.
Yes, Mr. Mazen. Hello, everyone. Today is the 1st of September 2024. We at the Society of Petrophysicists and Log Analysts, SPWLA Iraq chapter, are pleased to welcome you and to have joined us today. My name is Muhammad Jawad Zain Al-Abidin, VP of Technology at SPWLA Iraq chapter and Senior Faculty Member at Petroleum Engineering Department, College of Engineering, University of Kirkuk. The 7th webinar in 2024, Multi-Array Production Logging Analysis, utilizing Emeraude software of KAPPA Engineering, will be presented by our speaker, Mr. Nicolas Kotlar. Welcome to you again, Mr. Nicolas Kotlar. During the presentation, we will send a link in the chat box to join this SPWLA Iraq chapter on LinkedIn. Thank you, and the floors to Mr. Mazen.
Thank you, Doctor, for the introduction. Okay, I'd like to welcome our attendees, welcome our presenter. Okay, and Mr. Nicolas, you can start your presentation.
Okay, thanks, Mazen and Mohammed. Thanks for having me in your series of webinars and also to help spreading the voice to the petrophysics community in Iraq and the Middle East in general and worldwide in general, because I know that your webinar is watched by people not just from this region. I see the names. So let's get started with the array PL analysis presentation. We will be using Emeraude. I'm going to switch to the software in a few minutes. Just to mention, Emeraude is an integrated case hall logging package, right? It's not just a production logging software. In last year, in this series of webinars, we did a number of presentations. I think it was on multi-finger caliper, on cement, and so on. So if you see here, up here, you can see the techniques, the case hall logging techniques that we handle in Emeraude production logging for conventional and horizontal wells, DTS and DAS, right, including thermal modeling, multi-finger caliper or internal radios from ultrasonic, spectral noise, pulse neutron, cement logs, sonic, ultrasonic, radial tools, and so on, magnetic thickness and ultrasonic thickness as well, and a number of tools for reservoir characterization, like a post-processing of PLT interpretation, basically. So this is how Emeraude looks like for an integrated case whole, like production logging, cement, noise, 3D display, and so on, right? So this is how Emeraude looks since 2021. Okay, so let's go to the topic of the day, production logging with array tools. And the objective, although we will see that array tools are mainly used for highly deviated or horizontal wells, the objective remains the same as in our previous webinar, right? So the objective of PLT is to answer these three questions, right? Imagine that this is your completion. You have two perforations. You may have 5, 10, any number of an open hole completion. So you typically measure your surface rates. You may measure your total oil, water, and gas at surface. But you want to know from where is it coming from, right? So you want to answer these three questions, right? So what is the fluid? What is it oil? Is it water? Is it gas? That is coming from where, right? Is it from the upper perforation, from the bottom perforation? Is it coming from somewhere it shouldn't be any inflow, like a leak, for example, right? And then finally, the how much is the quantification, is the rate, is to put this knowledge of the fluid type and from where, and the amount in a profile like this, right? As you can see here, this is the typical cumulative flow profile and the contributions flow profile telling us, well, in this case, for example, this well, you can see that the bottom 3 layers produce water. So you can imagine the type of measures that you may want to take after this, right? You may want to set a plug, if you can, at this depth and get rid of the water coming from below, right? So this is why we do PLT, right? So just to go to array, I want you to understand basically the hypothesis behind conventional and why conventional is not suitable for highly deviated wells. So if you remember, this is your PL2 string flowing here in a single phase or multi-phase well. What tools do you see? What models? Well, you may see a full bore spinner, but what really do you need here in an array tool, in a conventional tool for computing the flow profile? Well, it will really depend on the number of phases that you have, right? So we said that for conventional, right, the basic, even for a single phase case, you only need a velocity, right? You're just trying to solve one equation in this case, right? You're trying to solve the total rate. Do you remember the previous slide that showed this, right? This is the total rate, right? This is barrels per day, right? So the total rate, we said in this case, is the mixture velocity, the velocity or the average if it's single phase, times the area of the pipe, right? So that's what we do in single phase. Now, what happens if we have two phases, right? If we add a second phase? Well, now from the total phase, let's imagine that now we have two different fluids. Let's say that the total phase, the total rate, sorry, is composed by oil and water, right? Or water and gas, right? Any two phases, any combination that you want to do. So for that, we need to split this total rate into the two phases. And one of the typical ways is to use a density or a hold-up tool. But this is what we did in the previous webinar, right? Finally, if we need a if we have a third phase, we need a second independent fluid identification tool. So imagine for the two phase, you use the density. Now for the three phase also, apart from the density, you will need a hold up tool. And I think in the previous webinar, we used capacitance, right? So those are the measurements that we need. But what are the big what is the main hypothesis of this of conventional PL? Well, the main hypothesis is that we have distributed flow, right? As you can see here, a cross section of the pipe at certain depth. Imagine we make a cross section, and we know that our tool will be centered here, right? So this center tool, we can say that is indeed measuring this mixture velocity that we need, right? It's mixture, right? It's partially affected by the water, partially affected by the oil, right? And also, if we run a density tool, for example, we can say that the density that is measured is actually a mixture density. It's a combination of the whole lap of the oil, in this case, times the density of the oil, plus the same for the water, right? So that's only possible, right? When it's only possible when we have mixed flow, right? And this is necessary. The condition of mixed flow is necessary for the conventional PL workflow, not just for the densities, but if you see here, the total velocity, as we said, the total velocity, the mixture velocity times area, right? This one is, we said that is equal to the rates of the oil and the water. The rates of the oil and the water, how are they? Well, the velocity of the oil times the area of the pipe, but the oil doesn't flow throughout the whole cross-sectional area, but you need to add also the holdup of the oil, right? Plus the same for the water, the velocity of the water, area of the pipe, water holdup. So can you see now that, well, I can get rid of all the areas here. So it shows that the mixture velocity is equal to the oil velocity times the oil holdup plus the water velocity times the water holdup. So again, the velocities are respond in a holdup weighted way, right? So this is telling us you really, if you want to use these two equations that are the basis of conventional PL, you need to be in mixed flow. The tools needs to look at mixed flow, right? So this is what I was just explaining, to go from velocity and density into the final output. If we want to solve these two equations, what we need are these mixture velocities and the mixture holdups, right? The only way we're going to get this from conventional tools, again, is if the fluids are distributed, right? Doesn't matter if I measure a bit here or a bit here, that is, I'm still getting a proportion of oil, a proportion of water, and this proportion is hopefully representative of the holdup of the two phases, right? And then through the use of multi-phase flow correlations, the slippage velocity, we can get to the final answer. This is what we did last time, so I'm not going to spend more time on this, right? So let's look now what happens when we start increasing the deviation, right? Well, you can start play at home by mixing oil and water, and you will see that the olive oil will go to the top due to buoyancy, right? Lower density. The lighter phase will move to the high side of the cross section, where it will travel faster, right? Higher slippage velocity at the beginning, right? So and ultimately, you know, if you have like a three-phase flow, you could have water. Let's say that this is oil and this is the gas, and red oil here. But okay, so what happens with a conventional tool in this scenario? Well, the conventional tool, hopefully centered, right, will be here, right? Do you see where the tool is? The tool here is affected. This is a continuous spinner. This spinner that we want in conventional PL to measure mixture velocity is actually measuring the water velocity in this case, right? It's in the heavy phase, right? The light phase is moving at another speed, right? And if imagine that here we can measure the density will also be the density of the water, right? So due to fluid segregation, this is not a full stratification, but it's a partially segregated flow. We can see that these tools do not measure average properties necessary for the conventional production logging workflow, right? So that's why we need this type of tools that we are going to see today. So what are these tools? Well, they look like this, right? So instead of having a single spinner, what you see here in this particular case are 6 spinners circumferentially, let's say, radially distributed, right? These are, while this spinner, this flow meter, sorry, this one can be like 2.5 inches, right? These ones are, here I have one in my hand. This is a mini spinner. You can see it's the size of my finger, right? So you get 6 of this, for example, right? So like this, right? Circumferentially distributed, right? The first tool that we are going to use, actually, the spinners are and hold-up probes are not circumferentially oriented, but are like this, axially oriented, right? So you have one spinner here, another one here, and so on, right? So these are the 2 main options that we have in the industry nowadays. So in terms of flow regime in horizontal wells can be very complex, right? In most of the cases, we assume a level of segregation, right? And depending on the fluid velocity, you can go from fully segregated, what we call a stratified flow. The segregation, if you have higher velocities, higher shear, efforts, right, stresses, we can get distributed and ultimately very high velocities, even miss flow, but this is not a very common condition. But in any of these scenarios, having a centralized spinner, right, imagine centralized spinner here on the low side of the pipe would not be convenient, right? And also, this is based on deviation. This is, for example, perfectly 90 degrees. This is decreasing the deviation. This is increasing the deviation. You can see that it can have a huge impact on the hold-up and velocity distribution. This is something that we will see in the first example. Okay, so we are going to go to Emeraude now, just to mention that, well, I've seen in the schedule of this series of webinars that you had presenters from different tool vendors and different service companies. So you probably know FSI. This is the SLB tool that we are going to do the first example. So in this case, as I mentioned before, this is one of the axially distributed tools like this, right? And then in one side, you can see there is like a triangle. On one side, it has 1, 2, 3, 4, and 1 on the tool body, so 5 mini spinners. And on the other side, it has 6 hold-up probes, electrical and optical for water and gas hold-up, right? So we are going to do the first example with this one. If we have time, we will see an example with maps, right? Or just a couple of images with maps. But there are other tools in the market. I saw that you had a presentation from Baker, another presentation from OpenField. So you probably learned about this, the PI and the FAST tools. Okay, so let's get started with Emeraude. There we go. So here we are in Emeraude now, and we are this is a horizontal. You can see for 4,000 feet MD in the horizontal length. This is an open hole completion, right? So this well is not perforated. And if you have dealt with this type of data in the past, you may know that there are, instead of having 1 spinner and 1 density, now you have 5 spinners or 6, and you have 6 or 12 hold-up probes. So a lot of data, right? So what you may want to do is to use this, what we call templates, right? Instead of 1 by 1 selecting the channels, you can see the templates. We have templates for all the main tool vendors, right? You can see Baker, Halliburton, OpenField, and in this case, SLB, right? We're going to use this, what is called the full layouts. And we're going to go straight to some of the FSI layouts, right? So you can see FSI layouts for spinners, for hold-ups, and so on, right? So for example, I'm going to start from template FSI electrical probe view. So electrical probes, these are, the tool contains 6 electrical probe. So what they do, right? So there are basically two electrodes very close together, as I'm showing here. All right, imagine one electrode emits a current, and you measure the voltage difference between the two, right? So you know that Ohm's law, voltage is equal to current times resistance, right? So based on the resistance, you can discriminate whether this is water or hydrocarbon, right? This is a water hold-up probe, right? So here you can see what I'm showing in these 5 channels. Can you see the probe 0, 1, 2, 3, 4, and 5, right? So if we remember how this tool, how this tool look like, it's like this, right? So the probe 0 is on the tool body, and as we go up, is probe 1, 2, 3, 4, and 5. So this is what you see here. Can you see probe 0 on the tool body is measuring 1, right? 1 on water hold-up means that it's immersed all the time in water, right? And can you see as you go up in this triangle, as you go up, the amount of water starts to decrease, which makes sense, right? Knowing that this is likely to be a stratified flow, right? So from 100% water, we go to pretty much 0% water, right? If you want to see how the tool looks like, click here on tool and multiple probe. And again, this is a triangle, right? So the probe position 0 is on the tool body. And as you go up, right, is 1, 2, 3, 4, and 5, right? Similarly, I mentioned that there are optical probes for gas holdup, right? So I can bring this here, FSI optical probe view. And I click OK, and you can see there are these 6 probes from 0 to number 5, and they are all 0, right? Meaning in this particular case, there is no gas at downhole conditions, right? So we have a water oil distribution. So we can pretty much the gas probes, we can discard them in this particular case. So if I come back here, I explain where is the low side, where is the high side, but definitely it doesn't look, it's not easy to show the fluid distribution. We can use a number of images, right? So I'm going to click here on new and select image view. And what I'm going to do, I'm going to plot the FSI holdups, right? You can see here the FSI holdups. There are 2 passes in this case, just one down, one up. Let me start with the down pass. So I'm going to call this image FSI down 1, right? And that's it. I click OK. So what are we showing here? And let me decrease the size of this track. So what are we showing here? Can you see that there are 6 bands here? 1, 2, 3, 4, 5, and 6. Each band shows the holdup distribution in the probe position 0, so in the tool body, until the top, the probe at the top, right? Probe number 5 in this case, right? So this is basically how this is showing that there is stratification, right? And you may still struggle to see if you are not familiar with these images. You can right-click and select cross-section, right? When you select the cross-section, what you see here is the pipe orientation. Can you see this in gray? Is the pipe. If I hover over, can you see that the pipe is sort of tilting? It's moving up and down, right? So it's showing the pipe orientation, and it's showing other things here, right? So in blue, between blue and green is showing the holdup distribution, right? So here you can see, well, there is a bit more of oil at this particular depth than water, right? You can go up and down, right? If I go right at the bottom, here, for example, here, well, you can see very little oil, right? So you can start quantifying how many probes are immersed in water and how many probes are immersed in oil. And if you know the geometry of the pipe and of the tool, you basically know the holdups, right? The cross-sectional holdups. So this is what we're doing here, right? So I'm going to exit this one, and a similar way, I'm just to compare, this is the FSI image for the down one. I'm going to do the same for FSI up one, right? And well, up to is called, it's the same. There we go. So these are the two images, which are very consistent, right? They are pretty much showing the same, right? So in this case means that, because in some cases, especially horizontal wells, if you use coiled tubing, that you get swabbing and searching effect, depending if you go up or down, the measure holdups can actually change, right? Another image that may be of interest here, if you click New and select cross-section view, is these little cross-sections, as I'm going to show here, right? So the cross-sections are quite good because quickly show the holdup distribution at any depth. And you can make more by decreasing the width of this track. Can you see? Now, at a particular depth, you can see what is the holdup distribution in the circular profile. So this is very, very handy to quickly understand how the holdups are changing from bottom to top of the lode. Okay, so the last set of sensors that we're going to see are the spinners. So we have, if I go here to FSI spinner view, we can see now we can see the, let me get rid of some tracks. We can see 5 spinners, right? The data has been cleaned already. You can see some missing intervals of data. So it has been cleaned, right? So each spinner measures RPS, right? So remember the spinner I'm showing here, revolutions per second. We want to obtain velocity, right? So we need to calibrate. After calibrating, we are going to, we can calculate the apparent velocity, right? In cases like this, if you see the values, right? Let me show you. So here, where I'm pointing with my cursor, bottom left corner, I can see the value, or you can point, use this show pointed values, right? And see the values at a particular depth of each spinner. You can see that from spinner 0, that is 3.9 something, 4.3, then 7.1, 12, and 13. So the RPS increases from bottom to top, right? So this is telling us that the lighter the fluid, right? If we go from the bottom that we have water to the high side that we have oil, fluid velocity increases, right? What we expect for stratified flow. There is another image that shows that. If you click image view and change this to velocities, let me increase a bit the amplitude like this, and I'm going to increase the spacing as well. You can use an image like this that shows basically where is the peak of the velocity distribution as seen by the spinners. Okay, but by the way, something that I didn't show here is that when you look at the cross sections at a particular depth, apart from showing the holdup distribution, these points in yellow, these are the velocities as seen by the spinner, right? So you can see that on the low side of the cross section, the velocities are lower. On the high side are faster, right? This is what we expect for stratified flow, right? Okay, so let's complete the interpretation now. We're going to click information here to remember so far we did like a quality check, the images. Now we need to start the proper interpretation. Classical, in Emeraude terminology, classical means PLT essentially. We go to the spinner tab, that the only spinner available are the 5 FSI mini spinners. Remember, as I said here, we need to obtain the fluid velocity, right? To go from RPS to fluid velocity, we need calibration parameters, which we typically obtain through a calibration crossplot, right? Passes at different cable speeds. Here in the horizontal, we don't have, right? So for this particular case, what I'm going to do is use constant values. If you select constant and this edit, you will see what are the slope and the threshold as informed by Schlumberger, by SLB, for these FSI spinners, right? So these are the values, right? So I'm going to use this to compute the apparent velocity. Click OK. Reference channels, as always, I need temperature. to compute the PVT properties, I'm going to select the down pass. And also pressure, I need to compute the PVT properties. So I'm going to select an average of both passes. There we go. Okay. So in Emeraude, remember, always follow the options. So we just created the interpretation. Remember that here we said, okay, we need to compute the velocity. For this, we would need to calibrate. But we already enter constant calibration parameters. We cannot calibrate, so we can skip and go straight to VUp. So I'm going to click here on VUp. This is the apparent velocity. Click OK. And there you go. Can you see on the left side, I have the FSI spinners, and the units are RPS. So these are the revolutions per second, the raw data measured by the spinner. On the right, I have the FSI spinner velocities, right? The computed velocities. So now I know actually what's the fluid velocity as measured by each individual spinner. Okay. So as we are nearly there, you can see we computed the apparent velocity. Again, the next option would be to fill the PVT parameters. So let's go here. We definitely have water, right? Click on water here. And we have oil. So I'm going to keep my saturated oil. In Emeraude, you need to go through this. This is a black oil PVT model, so you need to go through the different components. You can see water is asking for the salinity. I'm going to use default PVT parameters, which I don't recommend because obviously the result is going to be affected by this. Having said so, the impact on wrong PVT parameters when in horizontal PL is not as severe as in conventional PL, right? Because in conventional PL, you use a mixture density tool to compute to make the split of the hole laps. Here, you're using direct physical measurements. So at least if you have a wrong PVT, it's not going to affect your downhole calculations. What is going to be completely affected is the way you convert your results to surface, right? That's going to be very wrong because of the formation volume factors and so on. So anyway, I'm going to keep this constant. And now is the key step in horizontal production logging interpretation. That is what we call the MPT processing, right? So what do we do in this MPT processing? I'm going to show you a slide. Okay, so in the MPT processing, imagine that this is our log, right? Thousands of meters. So what are we going to do? Well, we're going to cut many slices, right? Like this. Imagine that you go with a knife and chop slices every 30 centimeters, 1 foot, 0.5. You decide how many what's the sampling rate that you want to use, right? And in each of these, what we're going to map the measurements. So here there are 12 circles, meaning 12 measurements. So what we really want to do is imagine we want to map the water hole lap. What's a water hole lap if from 0 to 1 for each of these probes, right? So this particular probe down here is fully immersed in water. So if we map this value versus the height of the cross-section of the pipe here, if we map this bottom value, it's 1, right? And then this one, well, this one is also 1, this one is also 1. And if we continue like this, we see that all of these are 1, and then we are in the transition, and then finally, the measurements are 0. There is no water up here, right? So we are mapping these measurements. And when we map these measurements, we can use a function to describe how this looks like. And we're going to do that. We're going to create a function of the water holdup, of the gas holdup. Well, in this case, there is no gas, but imagine them for a generic case. And also the velocities, right? We're going to do this, right? So this is the first thing we do. At every cross-section, we we describe how it looks like using a function, right? This function, as you can see here, I use like straight lines. So this would be linear interpolation, right? But you will see that as we treat this as an error minimization, we can fit any curve, right? You could fit a spline like this, right, to make it more physical. There are proprietary algorithms for Schlumberger. There are the so-called MapFlow, Prandtl, and so on. And the good thing is that you can stack many passes, right? Imagine if you have two passes, like in our case, with different relative bearings. Now you can use both in combined mode and generate like a pseudo one pass with double the number of probes. So what do we do with this function? Well, how do we use this function? Well, the way we use this function, remember, we have the holdup map like this. Well, we can do numerical integration, and instead of having a curve, well, we obtain a single centralized holdup value, water holdup, gas holdup, and oil holdup, if you want, for at every particular depth. So this is like a smart holdup calculation at every depth. And then we, as in this particular case, we also get a velocity map. Imagine this scenario, right? Here you know that you are in water, right? This part of the pipe is immersed in water, but now you also know at what velocity this water is moving. You can see the velocity here. Okay, so if you know the area of the water times the velocity of the water, what you know essentially is the water rate, right? Remember, velocity times area is rate, right? So you can find the rate. So through numerical integration, we multiply holdups times velocities and obtain the rates, right? So this is what we are going to do in the next here now in the next part. There we go. Oops, not this one. There we go. Okay, let me get rid of some tracks so I clean up this a bit more. So as I was saying, I'm going to go to the MPT processing. Again, in Emeraude, the key is to be systematic, right? So you start here from the top, FSI, and these are the different sensors included in the FSI. Gas holdup, we said there is no gas, so you might as well ignore the FSI gas holdup, right? This is the interpolation method that we're going to use. Remember, I said, well, it can be linear, it can be a spline, can be a proprietary algorithm like Prandtl. Let me start with linear, right? Also, the interval, every how many feet or meter, we are going to chop a slice, right? Phase constraints, right? In this case, the phase constraint, there is no gas, so you can set the gas holdup to 0. And then finally, there are other physical constraints you can add. As you are using error minimization, you can add other physical constraints. So water holdup decreases from bottom to top. This means from bottom to top of the cross-section. This can also be said low side to high side of the cross-section. So this is what's happening here. You see the stratification. We made the cross-sections, and we saw that the flow is stratified. So you can force this. So in case one probe locally fails, the algorithm will just ignore it. Finally, these are what passes. In this case, we created the images for both. So I'm going to use both, right, in combined mode. Okay, so that's it. I'm going to compute the results. Here, what it's doing, remember, first is mapping, and then it's doing this numerical integration to compute at every depth, to compute an average water and oil and gas holdup, and also the same for the rates, right? So that should be done very soon. And that's it, right? Here you can start to see many curves, many curves, right? I'm going to get rid of some of these curves. Let's go straight to the point. I have here the oil rate match and so in Emeraude, if you remember what it says when a channel ends with match, means that this match will be used for computing the final flow profile, right? So really here, can you see we have the oil rate match and the water rate match. So the results are this is the result, basically, right? The oil and the water rate at downhole conditions, right? This is the result, but we still want the typical QZT and QZI. We want to know from what remember, this is an open hole completion, so there are no perforations, right? So we still want to allocate the oil and the water, so the contributions from different layers, right? So for this, I'm going to use I'm going to set myself here QCalc zones, and then an interactive definition. I'm going to say, well, in gray here, I'm setting rate calculation zones, and in between these rate calculation zones is from where the rates can actually change. In blue, these are the so-called inflow zones. So the inflow zones here, I'm being arbitrary based on what I see that there are changes in rate. In your case, you can use geological information as well. Some other good source of inflow zone for inflow zone definition is the temperature that I didn't even show you. In this case, how the temperature look like. So here, that's it. What I'm going to do next is just click on rates, right? Here is the rate calculation. Slippage, this is the slippage correlation. Do we need to impose any external slippage correlation as we did for conventional? Well, no. Why? Because here we are measuring directly the water velocity and the oil velocity. So we are really intrinsically measuring what is the slippage between them. So constant slippage, not impose anything. And that's it. I'm going to set to click OK and compute the final profile, right? So this is the final, as you see, the QZT, and this is the QZI, the contributions coming from where we set the blue zones, the inflow zones in between the rate calculation zones, which mostly looks okay, but there is something that here doesn't make much sense, right? That is, this upper inflow zone produces water and injects oil, right? This is a downhole separator, right? A layer cannot produce one phase and inject another phase at the same time, right? It's either positive drawdown or negative drawdown, right? So this is a consequence of the calculation method that we use. So we just go here to rates, right? Contributions, and we are going to set this we're going to force Emeraude for all the contribution signs to be positive. And then click on global improve, and there we go. Okay, so here you can see we got rid of this silly, let's say, negative oil, positive water. Right, and these are our final. This is our final cumulative and contributions that we obtain by matching directly the results of the MPT processing. One thing that I wanted to show. Do you remember? If I click here on new image view again, another image view. Now I'm going to use the combined, right? Combined. Remember that the MPT processing, we said, well, let's use the up and down pass, right? As the well is stable, the measurements are good in both passes. Let's use the combine, right? And see how it looks like. So when I obtain this image, can you see it looks quite similar to the image of the down one, right? But this is made by two passes. If I right click and select cross section, can you see now that instead of having 5 spinners as I had in the previous case, now I have 10, right? I have double the number of spinners, right? Why? Well, and also instead of having 6 hold-up probes, I have 12, right? Because what you're saying is, well, use the two passes as if they were a single pass, right? And in this case, that the relative bearing between the two passes is quite different. Where is my relative bearing? Here. This is my relative bearing. Is quite different, right? The angles are different, so the proposition will change, which is beneficial for this type of interpretation. Okay, so this was the interpretation of a tool like FSI in a nutshell. You can see that the processing is straightforward in terms of the next step to take is follow the options, right? But in reality, for the ones of you who are in this business, you know that this type of measurements, what you need to do quite a lot is quality check, right? And also, as this, let me save this as a snapshot. So there you go. And also, can you see here, electrical probes? Here, we are already measuring the water holdup. This is the water holdup from 0 to 1, so 0 to 100%. This doesn't happen for every single tool. So I very quickly, I'm going to go to the other type of tool that is called maps, right? Maps, this, what I'm showing here is resistivity probes, right? So there are 12 of this, circumferentially distributed. So these tools are here. It looks like this basically, but this is a capacitance, but looks like this. So 12 of this. Can you see that the values in this case are 0 to 1, but these are not directly holdups. These are normalized resistance values, right? So this means that to go from a normalized resistance to a holdup, you need to do some quality check. You need to do some normalization. This particular case, if I click here on image view and obtain, can you see now seems like I have another tool that is called CAT, capacitance array. But for now, I'm going to select the RAT min, right? I'm going to call it RAT. And I'm going to select a suitable color scale, green to blue. And let's see how it looks like. There you go. Can you see from the 12 probes, I obtained something like this, an unwrapped image with the center showing the high side of the cross-section. Again, if you right-click and select cross-section, can you see now that center, right, that is green, right? And now the green is on the high side, right? So, and you can navigate like this, right? So in this case, this holdup distribution makes sense. And it's telling us that someone already did some calibration in this tool. So this is what you will have to do. And to show you, I'm going to go to another type of tool that is called the capacitance array tool. These are the raw measurements. Can you see? This is capacitance. So imagine this is this particular tool that I'm showing here with 12 probes. This is a three-phase holdup in stratified conditions. Look what happens now if I create the image, right? I click here, image view, and create the image for the cut, right? We call it cut. There we go. Now if I create this image, well, it doesn't look very good, right? Remember, high side in the center. So here we should have the light phase, right? So the water. And on the low side, right, the sides of this image, I should have the, sorry, on the sides, I should have the water. On the center, I should have the gas, right? If I make a cross section, right, can you see it looks like the gas is on the low side of the cross section? Well, this is telling us, well, this tool definitely requires some calibration. So this is a very typical step that you have to do, right? If you right click here on show tool calibration lines, you can see that, or let me go to tool information here. These tools like CAT and RAT require a calibration, require the analyst to identify the endpoints, right? So these are some base nominal endpoints that the tool provider gives us. But you as an analyst need to adjust this. So for example, the way you would do it, can you see? So this is, we definitely know that this is a three-phase flow here. So can you see the 3 lines? So what I will do here is edit tool calibration. I know that my lower level here interactively, I set this level to the minimum capacitance. Then the oil should be around here, right? And the maximum value that I see here is the gas, right? And this is something that you have to repeat for all of them. For this purpose, I use histograms as well to get a more accurate value. So what I'm going to do here, I'm going to click on Tool, Multiple Probe Tool, and come here to calibration of the cat raw data, cat R. And I'm going to, I have like a cheat sheet here with my actual values. So I already, I know what values to use for this. I'm going to Control C here and Control V them here. Okay, and okay again. And now after calibrating, meaning after setting the correct endpoints for oil, water, and gas, can you see now that this image makes complete sense, right? I right click here, I go and I see to this interval, for example, and I see the proper stratification, right? So that's how we expect the holdups to be. So in the previous example, in the FSI, I went straight to the computation just to show you the workflow. Now I'm showing you that some tools require some pre-processing, typically selecting endpoints, water, oil, and gas, or similar scenarios. One last image, and coming back to my FSI example, this one. If you click new, a nice image for horizontal, highly deviated and horizontal well is this well view, right? That shows, well, it's not so necessary in this particular case because the well is not fully horizontal, but can you see, this is the trajectory of the well, right? This is the TVD, right? And of course, in the vertical axis, you see the MD. So it's nice to come here to the browser, go to the interpretation, and from the input channels to drag and drop the holdup. So for example, I say my gas holdup, that by the way, there is no gas, and my oil holdup. And now I know what's my oil and water and gas in case I had distribution versus the TVD, which is very good because, you know, if you have like a well around 90 degrees, downhill trajectories, you may accumulate some water, uphill trajectories may form some sort of a small gas cap, if you call it like that. So it's good to take into account the trajectory. Okay, so that's pretty much it from my side. I'm now open for questions. Just to mention that in our website, there's quite a lot of material that you could use. We have this book in KAPPA that is called the Case Hole Logging book that has chapters on horizontal PLT, right? If you install Emeraude and you are new to interpretation, there are tutorials, 4 tutorials on PLT, including FSI, including maps, including FAST. So there is plenty of material for you to get started with the software. Okay, so I stop now and I'm available for questions.
Yeah. Thank you, Nicholas. It was a great lecture. Okay, for sure, it's have some advanced concepts. So for the people that do not have too much interact with conventional PLT, will not be an easy lecture for them, but it would be very useful. Okay, as start point. You have access to the chat box. You can see
Yes.
some people ask some question. If you like, take it from there.
Okay.
Thank you.
Okay, I see. I started from the first question. Can you share the link to this video? Really impressive for collaboration. I think it's the video of the AR that I was showing at the beginning. So you can find this on the LinkedIn profile of KAPPA. So if you go to KAPPA Engineering, you will see it there, or you can add me, and I have it on my profile as well. Yeah. So some comments. Okay, what's the meaning of hold up? Okay, so yeah, good point. As Masin mentioned, some more advanced concepts. Let me. So I was talking about hold up, but I didn't explain what the hold up was. So let's imagine here, right? So I freeze the production at certain depth. Now I start to count the area occupied here by imagine that these bubbles are the oil, the gas, right? gas bubbles here. So I start counting the area that these bubbles occupy, right? So I can do a pie chart like this, right? So I can say, well, now I know that my gas occupies this, right? So I'm going to call this my gas holdup, right? And the rest, if this is just oil, so this is going to be my oil holdup. So what is the holdup? Is the percentage of the pipe occupied by a phase. So the gas holdup, if you hear 25% holdup, it means that 25% of the pipe is occupied by gas in level area, right? So that's what it means. Okay.
Okay. Just a comment about this hold up, if you allow me.
Yeah, please.
So hold up is like a moving area. Okay. That means there is no change actually in the rate. Okay. It's just changing the how much oil taking place, how much water taking place in that who's pushing who's, okay, depending on degree. But the rate per each one will be mostly the same. Okay. This concept is for hold up. I believe I will recommend to go to KAPPA book. Okay, it's have been explained really nice. I believe you refer to this one. Yes. Okay, this is a very, very well written book. Okay, highly recommended book.
Yeah, yeah. As Masin was mentioned, the changes of holdups can be given by actual. Imagine if you have an inflow that changes the amount of oil and the amount of water. Of course, that will change the percentage of the pipe occupied by water and oil, right? The holdup itself. But the holdup can change, as Masin said, like a moving area, right? Because of changes in flow regime, right? Changes in deviation. Multiple things affect the holdups. Okay.
Yeah,
Okay.
like this well, it do not have too much change in holdup.
Yeah, in this particular well, there is no, but it's change in velocity, so that's why we get the nice shape. Let me continue. It says, if we forget to do the calibration, what kind of data will we have? When is the key point at which we can recognize the errors? Okay, so if I guess you are referring to the calibration, this type of calibration, the holdups will be off, right? So you will be getting much more water. You really need to, this has to be, you know, the quality check comes first, right? In this FSI interpretation, I went straight to the processing because the FSI tool exports the holdups directly. So this means that someone else did this step for you. Here in maps, you have to do it yourself, right? So this comes first, right? So it's key to do the quality check, the selecting the endpoints and so on. Same interpretation steps for other tools might be slightly different. So that's why I mentioned that in the if you are a KAPPA user, you go to the installation directory of Emeraude. Typically, when you install C program files 86 KAPPA, you will see the examples. So you will see, for example, if you want to do number 2 is on maps, right? So you will see the particular things of maps, right? So you will see how is the calibration done and so on, right? Number 3 is FSI, number 4 is fast. So each of them has a different. Let me see. Real-time data. I think this is real-time. This is a tractor job, so it's wireline. You said the calibration is done by standard table. What is the accuracy of this calculation? Okay, when we don't have multiple passes for spinner calibration, the only option pretty much that we have is to use nominal values, right? So these nominal values have multiple assumptions. These nominal values are typically obtained in single phase fluid, and this fluid tends to be water, right? So yeah, there is an uncertainty because the other fluids, oil and gas, have lower slopes and higher thresholds than the water, right? So there will be an error in the interpretation. So that's why it's good to, if you can do a number of calibration passes. This is also explained here in the book. It's not as simple in horizontal wells to do calibration passes, right? You can imagine that if this is your horizontal, can you do passes at 10, 20, 30, 40 meters per minute with tractor? No, you can't, right? So you may need to use an interval with low angle, so you can go with cable. So it's a bit more complicated. Okay. Okay, so that's it. It says, I want to install KAPPA. Can you help me? Yep. If you go to our website, you can you can download the software. You can download a demo license as well. So you can do it from our website.
Okay. I believe no more question on the chat box. Okay, just I want to maybe I have few points here. So regarding this example shows something really nice. That if we want to use multi-array tool, we don't have to do same operation as conventional PLT. We got 3 passes up, 3 passes down. Actually, we don't have to do so. Like all this interpretation, I believe done using only 1 pass down, 1 pass up, if I'm not wrong.
Correct.
Okay.
Correct.
Okay. So there is like some false concept. I heard it from time to time. We need to run maps or multi-array and we need to, and they put the program 3 passes up there. No, you don't have to do this one. Okay. This is for calibration purpose. We are dealing with totally different methodology for interpretation. Okay. Regarding calibration, okay, maybe you'll need some short interval, shut in the well, short interval, and you calibrate your this tiny spinner, okay, there above this zone and the oil zone mainly, okay, not during shut-in. And I want to highlight things that you already mentioned is about where is this example, and for the people that want to study this some real example, you show them where is this example placed. There is a document with extra details. Yes, this one. Okay. Also, you have all the losses, all the information. You can practice all type of reference of tool, maps, FSI, fast, if I'm not wrong, is there also. Okay. Fast is there, huh?
Yeah, number 4.
Yeah. Okay. So you'll have many multi-array tool. You can practice them. KAPPA is very generous, can give you the latest version, okay, for with 1 month license if you drop them email officially. Okay, KAPPA book is recommended. Okay, this few points in from my side was fruitful lectures. Let's say an advanced topic. Okay, we'll publish it on our YouTube. Dr. Mohammed, any last word from your side?
Yes, Mr. Mazen. Mr. Nicolas Kotlar, thank you for the insightful presentation. And dear attendees, we value your feedback on LinkedIn. Please use the link provided in the chat box. And I would like to thank everyone who joined SPWLA Iraq chapter today in this webinar. Okay, Mr. Mazen, the floor is yours.
Thank you. Thank you so much, Doctor.
you.
As Dr. Mohammed mentioned, it's will be nice to join our LinkedIn. I believe most of you join our LinkedIn page. If you like to provide the feedback, okay, on a private, on messaging, okay, or replying on our post, okay, that will be try to reply for everything. Thank you, Nicolas. Do you want to mention anything before we leave?
No, that's good. Thanks for having me. If you have, if the participants have any question, you can also contact me, kotlar@kappa.com. And then, yeah, as mentioned during this presentation, there is plenty of material in the KAPPA website to get started or to, increase your knowledge in production logging and case holding in general.
Okay, Nicolas, and let's hope we see you also next year in our next year theme. We'll be in touch for sure. So thanks for all our attendees. Thanks for Nicolas for his time for volunteering for this technical event. Thank you, Dr. Mohammed.
Thank you.
Thanks all. Have a nice day. Bye-bye.
Bye-bye.
Thank you all.